In this demonstration, I would like to introduce the Poisson distribution expression as a simplification of binomial distribution. So before doing that, let's have a review of the binomial distribution. So it is the most general model and applicable to all constant probability processes. If n is the number of trials for which each trial has probability of success p, then predicted probability Prx equal to x for counting exactly x successes in n trials is given by the expression ncx p raised to the power x and 1 minus p raised to the power n minus x. We solved the example and we considered that the defective items from a production line, they observed to appear with the probability 0.1, and the probabilities for getting defectives, any number of defectives in samples of 3, so they can be computed by the binomial distribution. So we have the video recording to according to that one. So which is available at this link, and I will leave this link. I will post this link in the video as well. So we also considered that how sensitive the binomial distribution shape is with respect to the given probability of defectives. For example, I have the same sheet over here. So if the value of the probability of defectives is changed to higher value, so we will be able to see the peak shifted towards the other side, towards the right side, which is towards the higher values. And if the values of defectives, probability of defectives is equal to the probability of good components, that is then the distribution of probability mass function is going to be symmetric one. So that is the sensitivity the binomial distribution shows for the probability of success, which is the one component of the binomial process. So it is likewise the probability of uh, heads and tails. So it is again 0.5 and 0.5. So if we consider the problem that the companies tend to improve on their processes, so they would like to collect more components and develop the larger samples. So if we consider the sensitivity with respect to the sample size and like the increasing the number of n, and if we go for the smaller values of the pro probabilities of defectives, then what's going to happen? So for example, if we consider this value to be 10, and this value is reduced to 0.05. So in this case, we have to consider a change in the possible outcomes, because now the x would vary from 0 defectives in a sample of 10, 1 defective in sample of 10, and so on. And we can get to the value all defectives, 10 defectives. So if we move on to calculate the binomial distribution, so then we will find that we can further go for the smaller values. However, the major part would receive from up to 3 defectives. So there is the probability of getting the number of defectives. The all other remaining possible outcomes, they have very less probabilities. So the peak is considerably shifted towards the left side. So the distribution is a positively skewed distribution. it is right skewed. We have a longer tail towards the higher values. So the probabilities are higher probabilities are shifted towards the lower values. This is a significant this is of significant importance, that the significant probabilities are shifted towards the lower values, and this is going to prevail if we go for further improvement in n and reduction in the probabilities of defective. So let's update this one as well. So I have to get to the select data option. So it requires editing the values. So it should be expanded towards these values. And likewise, the x values need to be edited to encompass all the possible values. So the distribution would look like this one. And let's see the value of mu, the average value. So mu value, I should insert the proper symbol so that the students learn how to find the symbols. So there is a gallery of symbols. So mu symbol. So in case of binomial distribution, we found that it is to be calculated from the n, the value n times p. So I can pick up the p value from here. So it is mu value is 0.5. So if we further go for the higher values, say 20. So again, we find the values of probabilities, they are uh, shifted more towards the smaller number of x values. So these are the values for importance. So this leads to uh, consider uh, this leads to the consideration of mathematical simplicity, whether there is such a possibility exists or not. So it was considered earlier that the calculation of binomial distribution, which requires the factorials, it is of considerable difficulty. But nowadays, with the available functions in the programming languages and the even the programmable calculators, people do not really feel that how difficult it was in the earlier times. So I write the mu value equals n times p, and if we consider that n is getting larger and p is getting smaller, so n is increased and p is significantly decreased. So we consider the calculation by binomial expression. So for some value of x, so we find that it is ncx and p raised to the power x, and q, which is the complement of p probability, it is n minus x. So this is reduced to n times, well, it is n factorial over n minus x factorial and then x factorial. This is p raised to the power x and y minus p raised to the power n minus x. So then this can be simplified to n times n minus 1 times n minus 2 up to so on, and there will be then n minus x factorial and divided by n minus x factorial times x factorial. So this will be eliminated, and then we consider that mu is equal to n times p. So p can be replaced by mu over n. Okay. So here it is n times n minus 1, n minus 2 times the final member which is going to survive here. It will be 1 unit value higher than x. So it will be x minus 1. And over here we have the x factorial, and times p is replaced by mu raised to the power x over n raised to the power x. So mu by n. And over here it is 1 minus mu by n raised to the power n minus x. Okay, so 1 over x factorial, and this is n raised to the power x. By inspection, we can recognize that the number of terms in the numerator over here, they are x terms. So we can distribute this n over all the n values. So n by n, n minus 2 by n, and so on to n minus x minus 1 and over n. Here is the mu x, and this will then be written by mu by n raised to the power n, and I write here the other part 1 minus mu by n raised to the power x. Okay, and then I uh, introduce here, this is mu by n. So I introduce here a divisor minus mu and a whole power of minus mu. So from calculus, and now we can apply the limit that in comparison to the value of probability, n is very large, and it is larger, n is very large as compared to the value x, and is large as compared to the value of x. So that leads to the limit application of limit as n goes to infinity. So here in all these expression, we will find a value of 1. So it is like applying the limit n approaches to infinity in comparison to the values of x, and uh, well, all these terms, like it will become 1 minus 2 by n, and so on. The next will be 1 minus 3 by n, and so on. It will become 1 minus x by n minus 1 by n, and there is mu raised to the power x, and okay, 1 minus mu by n and raised to the power x, and times well, this is very interesting that this part with the large value of n, this reduces to the Euler's number e, and with the power minus mu. So now with the application of these limits, so we have a simplification in the probability. Prx equals x, and it is then equal to 1 over x factorial and mu raised to the power x and e raised to the power minus mu. And this part is also reduced to 1 raised to the power x, and which is equal to 1, because in this problem x is an integer, so we have no problem in writing this one as equal to 1. So we have found a mathematically simplified expression which is similar to the expression that we obtained in the Poisson distribution. So, and it is all determined from the value of mu. So it means this type of expression can be utilized in the estimations of probabilities in case a problem is binomial and n is large and probability of success is in one trial is a small value. So then we can utilize this expression. This was considered as a much simplified expression as compared to the binomial expression in which the factorials and the other powers need to be calculated. So we can see that the mathematical expression of binomial distribution is simplified to the expression of Poisson distribution. So with this one, we can apply the recursive formula of Poisson distribution as well that we discussed in the previous lecture. I think it is available over here. Yeah, yes. So, which is also a computational simplicity that the probability at a value of r and r plus 1, they are related. Let's write that one more time over here. So with the expression of Poisson distribution, probability when x equal to x, so we can write e raised to the power minus mu, mu raised to the power x over x factorial. And for the next probability when x is equal to, for the next event, for x plus 1, it is going to share a part from the previous expression, so it will be x plus 1. So I can write it, so it is mu raised to the power x plus 1 over x plus 1 factorial, which is x plus 1 times x factorial. So which reduces the expression to the previous calculation when x was equal to x and times mu value and whole divided by x plus 1. So the calculations can be performed from this recursive expression. So let's demonstrate that. Let me demonstrate that one over here. So I move to the Microsoft Excel sheet. So earlier we have been doing all these calculations with the binomial expressions. And now let's see whether the Poisson approximation offers a, a facility which is mathematically proven. So now the estimates from the approximation. So for the same problem, I required the value of mu. And now this is the probability x equal x. And here, so for just for the indication, I turn that one to blue. So indicating that blue color column title means the binomial calculation, and P, so I convert that to Purple. Okay, so purple for the estimation using the Poisson distribution. So I use the approximation formula. Yeah. So I have to only evaluate for the first one, and then I can use the recursive one. So okay. So this one. So I calculate for the zero defective. So e raised to the power minus mu. So mu value is available at the G at the third location times mu raised to the power x. So, um, so mu G dollar 3 and raised to the power x value. So this is x and divided by x factorial. So x factorial, 0 factorial is 1. So this is it. So then I can apply the recursive formula. So which says that the previous estimate times mu over x plus 1 or the current x value. So here I'm going to use the recursive formula. So it says the previous value. So previous calculation times a mu value. So G dollar 3. So mu value and then divided by the current value of x, which is 1 more than the previous value of x. So recursively, we get this value, and then we can perform further calculations in uh, in recursive way. So we can then calculate the error. So error, so it is the approximate value from the mathematical approximation and from the exact one. So that's going to be the absolute error, absolute error. And let's convert that to percentage. So again, the reference value times the 100. So there is the less than 3% error. And as we go to the higher values, so okay, so then the error tend to increase, but actually this is due to the fact that the values are much less than the 100 value. So in such a case, the absolute error is more appropriate one. So we can find it. So that is relatively better measure. So we have the accuracy up to 2 decimal places. So this is a quite a fair kind of approximation. However, we have to consider that the probability of success should be very small and n should be very large. Let's test that one for a value, say 0 0.1 and 20. So we find that the errors are still smaller. So this is due to the fact that n is very, very large. If I reduce this value to 10, so again, we have these kind of the errors. So the sensitivity to the probability of defective and sensitivity to the sample size, they needs to be considered while applying the Poisson approximation to binomial process. So uh, as a rule of thumb, as a rule of thumb, this can be applied when n is greater than 20 and probability is fairly less than 0.05. So I also found that there is another criteria where when the mu value is less than 10. So we can apply the Poisson distribution formula as a mathematical simplification to binomial distribution. Please keep in mind, and I would emphasize it, that Poisson distribution is a characteristic distribution in itself. We discussed that one in the classes, that it is related to the number of events counted in some interval of time or interval of space, or it has certain kind of that normalization. This is about the modality of Poisson distribution expression, that it turned out to be a mathematical simplification of binomial distribution for the cases when n is large and probability is small. A similar description with calculations is given at this link, and I will share that link in the description of the video. In the second part of this demonstration, I would like to generate some of the mathematical characteristics from this simplified formula of Poisson distribution, which is not that straightforward in the case of a binomial distribution. So I stop this video at this point.